Hello everyone, thanks for taking the time to join us today for today's webinar, Test Standards for Hydrogen Refuelling Stations. The NEL webinars are sponsored by the UK Government's Department for Science, Innovation and Technology, DSIT. A recorded version of this webinar will be available to you along with a copy of the slide deck after today's presentation. We'd love to hear from you. So please submit your questions anytime during the webinar. You can find the Q&A panel on the left-hand side of your screen underneath the video feed. Your questions won't be seen by any of the other attendees, and we'll do our best to answer as many of the questions as we can. If we do run out of time, we'll follow up with any unanswered questions. My name's John. I'm a bid manager here at TÜV SÜD, and I've spent the last 20 years at the National Engineering Laboratory working as part of the Sales and Business Development team. As I said earlier, today we'll be discussing test standards for hydrogen refuelling stations, and I'm pleased to introduce you to today's presenter, Ravata. Ravata joined us 3 years ago and is a consultant for our Green Energy Services team. So if you're ready, Ravata, I'll hand things over to you.
Thank you, John. Hi, everyone. So I'm going to talk today about the TÜV SÜD National Engineering Laboratories field test standard, what we have done in terms of the design and the validation that we have completed in terms of the test rig itself towards the end of last year. So this talk will be essentially in 4 sections, and we will first look at the need for a field test standard, why we need to have it. Right, so as most of you would probably know, basically we had the COP26 that took place in Glasgow in 2021, and as part of that, the UK government published a 10-point plan for a green industrial revolution. And point number 4 on that plan was for the shift towards a zero emissions vehicles. And the reason for this is because transport remains the highest carbon emitting sector in the UK economy. And as you can see on the image on the right, cars and vans alone account for about 70% of UK's domestic transport CO2 emissions. And because of this, the UK government announced in 2021 a net zero vehicle emission mandate, and that looked at essentially setting out the plan for phasing out the sale of new petrol and diesel cars and vans by 2030. So, which then basically means that from 2030 onwards, all new cars and vans will need to have significant zero emissions capability, and from 2035 onwards, all new cars and vans that are sold in the UK will need to have 100% zero emissions at the tailpipe. The European Parliament also has set out similar plans with the European Green Deal and the Fit for 55 package. So because of this, in 2022, the European Parliament had voted for ending the sale of new petrol cars and diesel cars by 2035. So what are the means that we can, how can we reduce emissions from the tailpipe? So there are 2 pathways by which you could have zero emissions at the tailpipe. One is by having a battery electric vehicle, and the other is with a hydrogen-powered fuel cell electric vehicle. And both of these have been included in both the UK government and the EU's plans or strategies. Now, we can see in the road today, there's been a substantial uptake in battery electric vehicles with, for example, in 2022, in the UK, 1 in 5 new car sales was for an electric car, or was for a car with an electric plug, rather. Now, there are, however, certain circumstances where battery electric vehicles are not suitable. And one of the biggest drawbacks with battery electric vehicles is the limited range and long charging times. So this is where a hydrogen-powered vehicle can play a key role, because filling up a car or a van with hydrogen is similar to how we would currently fill up a car with petrol or diesel, whereby within 5 minutes of filling up the vehicle tanks, you could have up to 400 miles of range. However, there are many barriers as to why we don't see hydrogen-powered vehicles on the roads today. And as James May, the former Top Gear presenter, said during his recent review of his own second-generation Toyota Mirai, which is a hydrogen-powered first electric vehicle, the lack of hydrogen refilling infrastructure is possibly the #1 reason why we don't see hydrogen-powered cars in the roads today. A good example of this can be seen from the image that's shown on the right, which shows the current hydrogen refilling stations for cars in the UK. And essentially, you've got less than a dozen refilling stations spread across the UK. In Scotland alone, for example, at the moment, you've only got 2 refilling stations, and both of them are in Aberdeen. So there, as mentioned, there is a number of reasons why we don't see hydrogen refilling stations across the country, and one of them is due to the specific measurement challenges that arise at the refilling station's dispenser. And without addressing this issue for the measurement challenges, because of this, you cannot charge because you cannot accurately quantify the amount of hydrogen that is dispensed by the station onto a fuel cell electric vehicle, you cannot accurately charge the customer correctly. And as a result of this, it has a knock-on effect on the station owner and the hydrogen producers, and ultimately affects the government because of the potential loss in tax revenue. So a lot of research has gone into the safety for fueling hydrogen fuel cell electric vehicles, and most of the outcomes from these studies has gone on to become standards that are listed here. A good example of this is when you fill up a hydrogen-powered car with hydrogen gas, the temperature inside the tanks gradually increases due to the heat of compression and other thermodynamic phenomena. And because of this, many stations follow what's called the SAE J2601 standard, and this ensures that the first electric vehicle does not exceed its maximum temperature limit. So similar to this, you've also got the hydrogen tanks, and these are generally certified according to EC 79 and R134 regulation standards. And these ensure that the tanks are safe to use on the road, and it includes a multitude of tests that are completed on the tanks, which include, for example, a bonfire test. Now, in terms of hydrogen refueling to the car, the accuracy requirements are specified in the OIML R139 standard. We shall look at this standard in a little bit more detail now. So the International Organization for Legal Metrology, OIML, has previously had a standard that was applicable to measuring systems that were used to fuel vehicles with gaseous fuel. And in 2018, it was updated to include hydrogen. As shown on the table over here, essentially, you've got 2 classes, accuracy classes for hydrogen dispensing. You've got accuracy class 2 and 4, of which accuracy class 2 is the more stringent one. And the maximum permissible error for a dispenser that is used for accuracy class 2 is 2% for type evaluation. Now, in addition to the 2% maximum permissible error, the OIML R139 standard also has specifications for the minimum measured quantity, and for hydrogen, it is 1 kilogram. What you've got to bear in mind is that when you're measuring the minimum measured quantity, it becomes more difficult to accurately measure it, and therefore the standard has doubled the maximum permissible error when you're doing MNQ. But hydrogen refueling stations, however, have found is that essentially, because they're following the SAE J2601 fueling protocol, it is quite challenging in trying to meet the accuracy requirements that are specified in the OIML R139 standard. The R139 standard also does not provide any specifications for the test equipment that should be used, but most measurement institutes have favored a gravimetric approach for designing the test equipment. Now, what you've got to bear in mind is that unlike with petrol or diesel, because hydrogen is a gas, it's not possible just to use the flow meter as an individual system, but you've got to consider the whole dispenser as a complete measuring system. And as a result, the original standard in terms of type evaluation, it includes the complete dispenser as a whole. And because of this, we will have a look at, in the next couple of slides, the reasons for it. So, as mentioned previously, it's quite challenging in trying to achieve the original R139 regulations in terms of the accuracy requirements that are specified in it. And the reason for this is because one example is the hydrogen pressure that is supplied can vary significantly and could be up to 875 bar in pressure. Then another reason is because of this, for 700 bar refueling, you need to pre-cool the hydrogen gas to minus 40 degrees C. So because of these wide and extreme and varying conditions, most hydrogen refueling stations have preferred to go with a corroded flow meter. But what you've got to bear in mind is that there are additional sources of error at a dispenser which are not related to the flow meter itself or the flow meter's accuracy. So a good example of this could be considered as being the refueling nozzle itself and the hose. So essentially what you find is that after you finish filling up a station with hydrogen gas, filling up a car with hydrogen gas, then the station needs to vent the amount of the hydrogen gas that is in the hose in order to make it safe. And this amount of gas that is vented has actually been measured by the refueling station's flow meter, but has not been delivered to the end customer. So in terms of billing the customer, you need to deduct that amount of gas. Now, Appendix B in R139 standard has got ways of calculating or correcting for this vented gas. But what we have found is that there are a number of hydrogen refueling stations which do not apply for this correction. Another reason for the billing inaccuracies could be is to do with a lesser known effect, which is to do with the pressure and density changes that occur in the dead volume or inventory volume. So this is the volume of gas that is between the flow meter and the cutoff valve. So what happens is that essentially if you have, depending on the filling process that is being followed by the current consumer versus the previous customer, if you were to fill a car up with a different pressure, you end up with a different amount of gas that gets trapped within this region. And as a result, you end up with a billing inaccuracy. So a good example of this was with the study that was undertaken by Cezanne Exabit, where they did test at hydrogen refueling stations in France, Germany, and in the Netherlands. And what they found is that if you had partial fills, then the error due to the dead volume could cause issues in terms of billing, and have errors up to plus or minus 4%. And if you had minimum measured quantity, which is 1 kilogram fills, then the error could be up to minus 10%. So because of this, hydrogen refueling stations have looked at different configurations in terms of the design, and we shall have a look at 3 such configurations. So configuration number 1, which is shown on the left, is where you would have a flow meter installed at the 900 bar section upstream of the heat exchanger. Now, this is the ideal location for installing a flow meter simply because it would be seeing gas at a relatively constant near ambient temperature. However, as mentioned previously, you would then end up with a significantly large dead volume, which contains gas that was measured by the flow meter but not delivered to the end customer. So to counteract this issue of dead volume, what some refueling stations have gone with is to install the flow meter at the dispenser unit. However, in this case, what you find is that because it is installed downstream of the heat exchanger, the flow meter would initially be at ambient temperature and then suddenly start seeing gas coming in at minus 40 degrees C. And this varying temperature that the flow meter sees would affect the flow meter measurements accuracy. And as a result of the issues with configuration number 1 and number 2, some hydrogen refueling stations recently have gone with a system where they have installed both the flow meter and the pre-cool or heat exchanger inside the dispenser unit. And this way, essentially, you're having the flow meter seeing a relatively constant temperature and at the same time minimizing the dead volume. There are a couple of issues with this setup, though. One is that you need to have individual heat exchangers installed for every single dispenser, which could tend to be expensive. The other issue is that the footprint area for the dispenser would therefore increase, and which may limit the number of dispensers that you could install at a refueling station. So we've looked at some of the issues that are there in terms of flow measurement at a hydrogen refueling station. And because of this, TÜV SÜD National Engineering Laboratory took part in the MPM Metro Hive project, which looked at addressing some of these questions. The MPM Metro Hive 2 project, which is currently ongoing, actually builds on the learning from the Metro Hive 1 project. And its aim is to develop a traceable framework which can be used for testing dispensers at hydrogen refueling stations. And as part of this project, one of the activities we are looking at is to do an intercomparison test where a number of measurement institutes would be testing their hydrogen field test standards at a single refueling station. The UK Department for Science, Innovation and Technology provided the funding via the National Measurement Institute for the design and build of TÜV SÜD National Engineering Laboratory's hydrogen field test standard. And this test rig will be used in the Metro Hive 2 project. Right, we shall now look at some of how we designed the TÜV SÜD hydrogen field test standard. So the design basis for the NEL's hydrogen field test standard was that it should be suitable for evaluating hydrogen refueling station dispensers with respect to the ORIML R139 requirements. And in part 2 of R139, you have the details on the expanded uncertainty that should be used for the associated test method. And for example, it states that for type evaluation, you need to have expanded uncertainty that is 1/5 of the applicable maximum permissible error. So based on this, if you have a class 2 accuracy requirement, then the target uncertainty for the field test standard is 0.3% at 95% confidence interval. So what we've done is use the experience that we've gained with discussions from the other National Measurement Institutes on how they have built and operated their test rigs and designed ours based on that. So our test rig is also a gravimetric system, which has a hydrogen capacity that is similar to a fuel electric vehicle, a light-duty fuel electric vehicle. And based on this, it can therefore verify hydrogen with up from 1 kilogram up to 6 kilograms in capacity. It's also got the capability to verify H70 dispensers, and that is to verify dispensers which fill hydrogen up to 700 bar nominal working pressure. Now, because we're dealing with hydrogen at high pressure, we carried out a number of safety studies, and these include HAZOP, a hazardous area classification study, as well as a risk assessment which included a fault tree analysis. Now, as we are dealing with gas at high pressure, we have to conform to the UK pressure system safety regulations, And as we're dealing with hydrogen gas, we also need to conform to the DESIR regulations as well. The image shown here is a typical setup when we were to be testing at a hydrogen refueling station. Your test standard will be parked right next to the dispenser, similar to how a car would park up for refueling. And you would have the DAC and control system plus the vent stack a safe distance away from the test rig and the dispenser itself. Now, this slide shows some of the outcomes from the hazardous area classification study. And what we found is that in order for the test standard, which is going to be transported inside a trailer, to be classified as an ATEX Zone 2 area, we needed to have an LEV fan. Otherwise, what you found is that the zone becomes a Zone 1 area, which makes it very difficult to source suitable measuring equipment. The exit of the vent stack, however, will be a Zone 1 area, and therefore it's got to be a safe distance away from the rest of the test rig. This is a schematic diagram of the key components that are in the NEL's light-duty hydrogen field test standard. And essentially what we've got is an H70 receptacle, which is the same receptacle that would be used for refueling a fuel electric car. What would happen is that you would connect the hydrogen refueling nozzle onto the receptacle and fill up both the tanks that are shown in here with hydrogen gas. The amount of gas that's filled up in the tanks is quantified by using a weighing scale. And what you would do essentially is weigh the complete rig before the filling of hydrogen gas and weigh it after filling with hydrogen gas, and the difference in mass is the amount of hydrogen that has been dispensed. Now, once you've finished the testing, then we need to blow down the tanks, and the venting panel that's shown on the top right side is used to blow down each tank, and you've got two pressure regulators that are in series, which help to defuel the tanks. There is also a pressure relief valve there, which essentially limits the minimum pressure down to 20 bar, because going below 20 bar, what you find is that it damages the tanks, as well as there are a number of hydrogen refilling stations which do not allow filling if the pressure in the system is less than 20 bar. Now, once we finish our test, what happens is that we want to make the system safe. So at the end of the test day, we purge the tanks with nitrogen gas to ensure that the hydrogen concentration is less than 4%, i.e. less than the lower explosive limit. So as mentioned previously, the test standard is based on a gravimetric system or gravimetric principle, and as a result, the weighing scale plays a key role in the operation of the test rig. The weighing scale we are using here has a capacity for 300 kilograms of weight, and it has a resolution of 0.1 grams by enabling the 10x mode on the terminal. Now, as we're dealing with a weighing system that is needed to have a very low uncertainty, we are looking at also buoyancy correction as well. This is especially important simply because the type 4 tanks that are there in the test rig expand slightly when they're pressurized. The expression that you can see here is what we have used in the uncertainty budget, and it includes terms for the tank expansion as well as for the air density or buoyancy correction. This slide shows a summary from the outcome of an uncertainty budget analysis that was carried out for a 1 kilogram fill. And essentially what we found is that for a 1 kilogram fill, which is the minimum measured quantity specified in R139 standard, the expanded uncertainty of the test rig for K equals 2 is around 0.22%. That is, it can meet our target 0.3% target uncertainty. This uncertainty could decrease further, for example, if we were to include correlation, because a number of instruments are used for both before and after filling. However, what you've also got to consider is that for 700 bar refueling, because you've got hydrogen gas that comes in at minus 40 degrees C, there is a possibility that the pipework will have some ice forming around it on the outside. And therefore, if you were to assume, say, for example, 1 gram of uncertainty in the due to icing, then the uncertainty actually increases and could be increased up to around 0.25%, which is still within the target uncertainty of the test rig. So what you would need to do, obviously, is to do tests at a hydrogen refilling station in order to more accurately quantify the impact of the icing on the overall uncertainty of this test rig. The slide here shows a more detailed analysis of the uncertainty budget when you had a 1 kilogram fill. The key takeaway from this slide are the two areas that are highlighted in red. So essentially what we found is that the mass reading has the most significant influence on the overall uncertainty of the test rig. And it is followed by the uncertainty in the air density, which is, of course, to a much smaller extent. The next slide shows the impact if you were to have a 6 kilogram fill, which is the maximum capacity for the test standard. And in this case, again, the mass reading has the largest impact on the uncertainty. However, in this case, what you also find is that the pressure coefficient, which is used to calculate the tank expansion, has also a reasonable impact on the uncertainty. And the reason for this is because when you pressurize the tanks to 700 bar, the tanks do expand quite a bit and therefore affects the overall uncertainty budget. Right, we shall now look at what validation tests we have conducted on the gravimetric system for the test rig. So the validation that we carried out is similar to what the other measurement institutes had undertaken during the MetroHive projects. So essentially what we've done is to use a calibrated correlative flow meter and nitrogen gas to fill up the test rig to known mass of nitrogen gas and compare what the test rig gives against what the Coriolis flow meter is telling us. So in this case, what we have done is to use the same nitrogen panel that we have on the test rig for purging it. But the difference in this case is that we have also included a heat exchanger, and this was based on the findings from the other project partners. Essentially, what they found is that in order to get more repeatable results, it was best to have a nitrogen gas coming into the flow meter at a constant temperature. Hence the reason for installing a Coriolis flow meter, installing a heat exchanger to ensure that we, in our case, had 20-degree nitrogen gas coming into the flow meter. So the test that we carried out was undertaken inside the James Young building at NEL. But what we found is that because this is quite a large building, we had to have the test rig partially shielded so that we excluded or minimized the effect of draft or wind effects on the weighing system. The initial condition for each test was that we had to ensure the tanks were at 20 bar in pressure. And then we took the initial weight measurement and the flow meter readings. Next, we filled up the test rig with nitrogen gas and observed the flow meter's totalizer reading. And once we had reached the target totalizer value, then we stopped the nitrogen gas flow rate and then took the final readings, which was again the final weight measurement, the flow meter reading, and the ambient conditions as well. So this slide shows the test matrix that we did for the different tests with the verification process. And what we have done is essentially do a minimum of 5 repeats for each individual test. Also, what we carried out was a 1 kilogram minimum measured quantity test. That this was done for different tank configurations, for example, a single tank versus both tanks filled with 1 kilogram. We also did tests where we filled the system to its maximum capacity if we were to do a hydrogen refueling test. So for the hydrogen refueling, the maximum capacity is 6 kilograms. So we filled the tanks up such that you had 6 kilograms of nitrogen inside the tanks. Since there could be cases or options where we might only want to fill up the large tank, we did test with the large tank only, and again we went to the maximum capacity of that tank, which was 4 kilograms. The results that we are going to report next are based on the relative, are given according to a relative error of the flow meter, and it is defined as per the expression that's shown here. So you've got the Coriolis flow meter reading as well as the mass measurement from the test rig's gravimetric system. We carried out a total of 55 tests, and during each of those tests, we essentially ensured that the nitrogen gas flow rate was between 0.3 kilograms per minute and 1.4 kilograms per minute. The reason for this is because this was a range at which we had calibrated the Coriolis flow meter at NEL. The data that's shown on this graph is for all 55 tests, and basically the dots or the data points in blue are when you do not apply any buoyancy correction. The data points in red are after you have applied buoyancy correction. And what you can essentially see is that even though the tests were carried out inside a building, applying buoyancy correction has a small impact on decreasing the error. The two horizontal lines that you can see here are essentially the limits of calibration of the Coriolis flow meter that was used. The data points that you can see here are for the flow meter error versus the mass scale indication from the gravimetric system. And it contains data for the different tank configurations. So if you use just one tank, or if you use two tanks, or for example, if you use a smaller tank versus a larger tank as well. And as a result of this, because the tanks are installed in side by side, you could get some eccentric loading on the ring scale, and some of the scatter in the data could be due to that. So what we've done here is only consider if both tanks were filled with nitrogen gas. And what you can see essentially is that there is no distinct trend of error versus the amount of gas that you have filled. So, which is a good thing in one sense, because essentially you don't need to apply any correction or any correction curve as such. The relative high error, of course, what you can also see is that, for example, there is a high error for the 2.4 kilogram fill, and this is possibly due to an environmental condition effect, because what we found there was that the LDV fan in the James Young building wasn't operating at that particular moment for that test, and the fan would randomly rotate. And this, you could see the effect of this could be seen on the ring scale, where there were fluctuations in the ring scale. So essentially it showed that you need to have quite a stable environment if you want to basically have our target uncertainty. But what the key takeaway from this graph essentially is that the test data are within the mean error of calibration for the flow meter, and we can essentially say that the test standard meets a target uncertainty of 0.3% and therefore is suitable for use as a test method for ORIML R139. Now, the data shown here is when we used only the large tank. And in this case, again, what you can see is that there is no distinct trend of error versus fill rate. So again, because the data points are within the mean error of calibration for the flow meter, we can essentially say that, once again, we could even use the large tank only for verification of a dispenser with respect to ORIML R139. The data shown here is for a 1 kilogram fill, which is the minimum measured quantity as specified in ORIML R139. And what you can see in this case is that, what we found during the testing is that it was best to fill both tanks with nitrogen gas, simply because that way you minimize the impact of eccentric loading. We especially saw this effect when we were putting in reference weights at different locations on the test rig. So again, the key takeaway from this plot is that the data are within the mean error of calibration for the flow meter. And also because ORIML R139 states that for minimum measured quantity, the error, the maximum permissible error is doubled. Therefore, you're looking at a 0.6% uncertainty. And as a result, the test rig can therefore be used as a test method for minimum measured quantity, as specified in ORIML R139. Now, as mentioned previously, the flow meter that we used was previously calibrated at the NEL dry gas facility. So what we could do is use the flow meter as a transfer standard to compare the performance of the Coriolis, compare the performance of the dry gas facility against the NEL hydrogen filter standard. And what we've done here is essentially plotted the data for that comparison. But what you've got to bear in mind is that the dry gas facility operates on a flying start and stop principle, and therefore it essentially means that the flow meter is operating in a more ideal condition, as it were, because, for example, you wouldn't have any sharp flow profile gradients across across the test point. The pressure at which the flow meter was calibrated was also constant at 40 bar. But what the intercomparison test results essentially show is that the performance of the hydrogen field test standard is within the error and uncertainty limits of the dry gas facility, and therefore both test facilities do meet their target uncertainty. So what are the conclusions that we can make from the verification test? One is that essentially in order to minimize the uncertainty in the weight measurement, it's best to decrease the eccentric loading on the weighing scale, and therefore it is better to operate the rig with both tanks filled. The test rig, or the hydrogen filter standard, performed well, and in the comparison with the dry gas facility proved that the target uncertainty of 0.3% could be achieved. And because of this, we could say that the test rig is suitable for use as a test method that could be used to verify hydrogen refueling station dispensers with respect to the ORIML R139 standard, and this includes the minimum measured quantity fill, which is a 1 kilogram fill. What we also found out is that the test rig is quite sensitive to any changes in ambient conditions or environmental conditions, and therefore this is something that operators need to take into account when they use this test rig at hydrogen refueling stations. Now we shall finally look at some of the planned activities before ending this presentation. So at the moment, what we're looking to do is to complete some modifications on the test rig and obtain UK EX and EU ATEX certification. And this is crucial because we need this certification if the test rig is to be operated at a hydrogen refueling station. Then we're looking to participate in the MetroHive 2 intercomparison test, where a number of measurement institutes are going to test their test standards at a single refueling station. And finally, TÜV SÜD is looking to launch a joint industry project later on this year, and we are looking to determine and verify hydrogen refueling station dispensers in the UK with respect to the ORIML R139 regulations. Thank you very much for listening. So I'm open for the questions.
Thanks for that, Ravata. Yeah, we've got some time left, so let's go through some of the questions that you've posted. Let's start us off with a. Let's see now. Here we go. Right. Okay.
Sorry, John. Is there a way that I can see the questions as well?
Well, it's probably just quicker if I just read them out to you. Okay, the first one we've got is, let's see, how long does it take to complete a verification at a hydrogen refueling station?
Right, that's quite an interesting question. It's something which came up during a recent conference I went to as well. So essentially, the ORIML R139 standard has, in part 2 of it, it specifies the tests that need to be performed as part of certification. And it states that you need to do a full fill, you need to do a partial fill, as well as a minimum measured quantity fill. And for the full and partial fills, you need to do that at least 3 times. And the minimum measured quantity must be done at least once. Now, the problem is that when you're setting up a weighing system, as people would know, it takes time for the weighing scale to stabilize. So it takes at least an hour for the weighing scale to stabilize, right? Then you also need to consider that the hydrogen tanks cannot be blown down very fast because they cool too rapidly and you exceed the minimum temperature limit for the tanks. So it takes up to 1 to 2 hours to blow down the tanks. So after you do a full fill, you would need 2 hours, at least 2 hours, say, for example, before you can start with the next test. So you're looking at a number of days for verifying a single refueling station's dispenser.
Do we know yet or have any details yet as to how often we need to do that? You know, is that a once a year type thing?
Right. So that's another question. Yeah, so exactly. So again, it is down to each country. Now, what we found is that essentially UK at the moment doesn't have ORIML regulations in place yet for the dispensers. But in Europe, for example, France has it in place. And France has it for, I think they have gone with class 2 now. And they initially, because they want to get an idea of how the station performs over time, they initially had it where they need to be verified every 6 months. But now they have gone to once a year calibrations instead, or verifications instead, which is still quite a cost for the station owner because the station might be out of action for up to, say, a couple of days. Each dispenser is offline, essentially.
Yeah. And I suppose this sort of feeds into the next question I have here, which is what are the practical challenges, bottlenecks that hydrogen refueling stations are experiencing in view of obtaining OIML certification? So I think we probably touched on some of that, but is there any other bottlenecks that we see?
Yes. So essentially, exactly. So one is that they need to obviously make sure that they are applying the vent calculation correctly, because otherwise you have got a billing inaccuracy there itself, because the amount of hydrogen gas that is vented after each fill needs to be accounted for in the billing process. Then depending on how the station is designed, you need to take into account the dead volume effect as well. So you could possibly have, let's say, devices that are, or instruments that are installed in the dead volume area to account for the mass of hydrogen that is remaining in that section. But in addition to that, another bottleneck is the number of institutes that can actually issue the ORIML certificates. Now in Europe, you only have 3 notified bodies that can issue the certificates. So there is a bottleneck there as well, in addition to the whole process that it takes a number of days for verifying one dispenser.
Yeah. Okay. Next question I've got here. Okay. Given that heavy duty vehicles are going to be powered by hydrogen, and obviously I know that Aberdeen have got a project running with hydrogen powered buses. Is there a system to verify hydrogen dispensers for heavy-duty vehicles?
Right, that's a good question, because what we think might happen is that heavy-duty vehicles, it's more, let's just say, it might be more economical to have a heavy-duty vehicle running with hydrogen as opposed to a car, simply because having a heavy-duty vehicle running with electric batteries will not provide you the range that's required. Yeah, because heavy-duty trucks travel much further distances. So for the heavy-duty, what essentially has been happening is that the MetroHive 2 project is looking into that. And there are two measurement institutes. TÜV SÜD is one of them, which is looking to, or which are currently in the process of building a standard for heavy-duty vehicles. This is because, if you think of it, the light-duty vehicle standard can only measure up to 6 kilograms. For heavy duties, you could be going up to, say, 40 kilograms of hydrogen gas. So essentially, the test standard that's there for a light-duty vehicle is not suitable for verifying a heavy-duty dispenser.
Yeah, okay. Let's see, next question I have here. Right. How would calibration laboratories calibrate Coriolis meters used on HRS dispensers, given site conditions have hydrogen gas at wide operating pressure and, hang on, that disappeared from my, and temperature ranges? So obviously the conditions in the HRS are going to be different from the laboratory. So the question there is how a lab's going to cope with that.
Right. So for that, what happened is that it was looked into in the MetroHive 1 project. So the MetroHive 1 project had a test program that was carried out where essentially we looked at Coriolis flow meters that are normally used in a refueling station, but we calibrated them using nitrogen, using air, and using water, and checked to see how the performance was. So what we essentially did was use them at a stable condition, steady state condition, at the same flow rates that you would see at a hydrogen refueling station. So you can change the pressure. Say, for example, nitrogen at 40 bar and 20 degrees C is comparable in terms of density to hydrogen at 700 bar. So you could see the performance of the flow meter with nitrogen. And what we've essentially found is that the most Coriolis flow meter manufacturers calibrate using water, and that water calibration seems to meet the accuracy requirements that are specified in the ORIML R139 standard. So they are essentially suitable for the refueling station itself. The only thing you've got to bear in mind is that the temperature effects, because a sudden drop in temperature essentially affects the meter's performance.
Yeah, okay. I think a follow-on question from that was when we did the Coriolis calibrations at NEL, and what gas did we use for that, or what? That's a.
All right.
Yeah, what gas did we use for those calibrations?
Right. So at NEL, what we've used is nitrogen gas. So now when you're saying calibration, talking about the Coriolis flow meter calibration that was done using nitrogen gas. But the other project partners at MetroHive 1 project, essentially they did it with air and also with water. And what we found is that the results were, so the water tests were done obviously at a higher pressure, right? And essentially you could fit them on the same graph and see how they performed, and they were almost very close to each other in terms of their errors.
Yep. Okay. And someone's asking here, is there any details yet on when MetroHive 2 comparison test at a station will take place?
Right. So what I can say here is that it is actually happening as we speak. One of our colleagues is over at a station in Germany observing the tests that are being conducted by SESAM. So we are each going to go to the same station over the course of this year and do the testing over there. So it's happening as we speak. But the test results, I think, will be only published later on. Yeah.
So yes. Everyone needs to stay tuned. Yeah. Okay. Yes, exactly. Are we looking to design and compare a Coriolis transfer standard as part of this Metro High?
Sorry?
Are we looking to design and compare a Coriolis transfer standard as part of Metro High V?
Right, yes. So that is another measurement institute is looking at that as well. So essentially what they're doing is to have a master meter that could be used possibly to, instead of the field test standards, because as mentioned previously, a field test standard takes a number of days to do a verification. Yeah. So if you were to have a master meter instead, then you could reduce that time requirement. Yeah. But what you've got to still bear in mind is that master meter, the uncertainty of the master meter will be slightly higher than the primary standard, because ultimately you'll be calibrating that master meter against the primary standard. Okay, so the initial station verification still might need to be done with the primary standard, follow on by the master meter afterwards.
Yeah, okay. Let's see what we got next. We've still got a little bit of time, so right, okay. Did you record any embrittlement in your material? If no, what material was used to design the flow meter?
Right, so the flow meter is commercially available flow meter. We've actually gone with a tricom meter for the light duty, but an Emerson meter for the heavy duty, so that you could have different meters and see the performance of each. So there are a number of flow meter manufacturers who do supply Coriolis flow meters to the hydrogen refueling stations. And I think that I don't think the flow meters were named. No, in the Metro High 1 project, we didn't name the flow meters, but there were, I think, 4 different flow meter manufacturers that we tested from. Yeah. Yep. Now,
but obviously we don't advertise.
But you got to bear. Exactly. Yes. Right. So, but what you've got to bear in mind is that the test rig itself operates only for a short time period, so hydrogen embrittlement wouldn't be much of an issue. End of the day, right? So, but for the station, it might be a different case because it should be seeing hydrogen gas throughout its lifetime. Yeah. So, but what you've gone essentially with is the stainless steel tubing that is being used normally for hydrogen refueling stations, and gone with the kit that is essentially used for station as well. So it's all hydrogen certified piece of kit. Because you've got to make sure about that, especially since hydrogen is such a small molecule. Yeah.
Yeah. Question here is an interesting one. Did we consider any other metering technologies? And the example, this one's saying, for example, differential pressure. So we considered it. Did we consider any, or did we just go straight to Coriolis?
At the moment, we've gone straight to Coriolis because that's what hydrogen refueling station operators use at the moment. But it's something that we definitely would be keen to investigate the performance, because especially if to see how it really performs with varying temperature, because that's where we are finding one of the issues with the operating regime is that it's a sudden drop in temperature from ambient to minus 40 degrees. And how does a meter perform then? So yeah, it's definitely something which we'll be interested in studying.
Okay, right. Well, we could talk on this all day, I think, and the questions have been coming in good style. So apologies if we've not got to your question yet, but as I said earlier, we will respond and follow up on those. But we're almost out of time, folks. So thank you, Ravata. Thanks again for joining us. As I mentioned earlier, you will receive a link to the recording for today's presentation and a copy of the slide deck. Get in touch with us and let us know if there are any webinars, any subjects that you'd like us to cover. Probably this one will, a follow-up to this one is probably something that people will be interested in. It's great to hear exactly what your interests are, so get in touch with us. Feel free to get in touch with me or send any inquiries to info.uk@tuvsud.com. Visit our website on www.tuvsud.com/UK. You'll find some more details on there. And on behalf of myself and Ravata, thanks for your time today and enjoy the rest of your afternoon. Thank you.
Right. Thank you.